Good morning, everyone. My name is B. Varun. I am from CSC D section. Today's my tech talk topic is methods of differential constraints. The contents in my topic are introduction, description of the method, example, differential constraints method, example. Introduction to differential constraints. Differential constraints are a class of finite difference equations specified over functions from the power set of a finite set into the reals. We characterize the implication problem for such constraints in terms of lattice depositions and give a sound and complete set of inference rules. We relate differential constraints to a subclass of propositional logic formulas, allowing us to show the implication problem is CoNP complete. Furthermore, we apply the theory of differential constraints to the problem of concise representations in the frequent item set problem by linking differential constraints to disjunctive rules. We also establish a connection to relational databases by associating differential constraints to positive Boolean dependencies. Description of the method. Additive separable solutions in this case of two independent variables are sought on the form wxy is equals to phi into x plus phi, phi into y, equation 1. At at the initial stage, the functions j into x and y into y are assumed arbitrary and are determined in the subsequent analysis. Differentiating equation 1 with respect to y yields tau w by w tau y is equals to f into y, f is equals to tau y. It is equation 2. Conversely, relation 2 implies a representation of the solution in the form equation 1. Further, differentiating 2 with respect to x yields d squared w by dx dy is equals to 0. It is equation 3. Conversely, from 3, we obtain a representation of the solution in the form 1. Thus, the problem of finding exact solutions of the form 1 for a specific partial differential equation may be replaced by an equivalent problem of finding exact solutions of the given equation supplemented with the condition 2 or 3. Such supplementary conditions in the form of one or several differential equations will be called differential constraints. Example: consider a boundary layer equation for the stream function dw by dy into d square w by dx dy minus dw dx into d square w by dy square is equals to a into d square w by dy cube. Let us seek a solution of equation 1 satisfying the linear first order differential constraints. dw by dx is equals to phi into y. The unknown function j into y satisfy the condition of compatibility of equations 1 and 2. First stage, the successively differentiating equation 2 with respect to different variables, we calculate the derivatives. wxx equals to 0, wxy equals to phi naught y, wxxy equals to 0, wxyy is equals to phi double naught yy, wxyy is equals to phi naught YYY. Equation 3. Differentiating equation 1 with respect to x yields w square xy plus wxxy minus wxxwyy minus wxwxyy is equals to awxyy. Equation 4. Substituting the derivatives from 2 and 3 into 4, we obtain phi naught y square minus phi into phi naught y is equals to a into phi naught y. It is equation 5. It is a compatibility condition for equations 1 and 2. Second stage. In, in order to construct an exact solution, we integrate equation 2 to obtain w is equals to phi into y into x is equals to phi into y. It is equation 6. Third stage. The function y into y is found by substituting equation 1 and taking into account condition equation 5. As a result, we arrive at the ordinary differential equation phi naught y minus phi naught y is equals to a into phi naught y. It is equation 7. Finally, we obtain an exact solution of the form equation 6 with the functions y, j and y described by the equations 5 and 7. Boundary layer equation for stream function dw by dy d square w by dx dy minus dw by dx into d square w by dy square is equals to a into d cube w by dy cube. It is equation 1. Differential constraint dw by dx is equals to phi into y. It is equation 2. Differential constraints method. Consider a general second-order evolution equation solved by the highest order derivative d square w by dx square is equals to f into x comma t comma w comma dw by dx comma dw by dt. It is equation 1. Let us supplement this equation with a first order differential constraint. dw by dt is equals to g into x comma t comma w comma dw by dt. Let it be equation 2. The condition of the compatibility of these equations is wxxt is equals to wtxx. Differentiating equation 1 and equation 2, we find that dtf is equals to d square x g. Let it be equation 3, where dt and dx are the total differentiation operators with respect to t and x. dt is equals to d by dt plus wt into d by dw plus wxt into d by dwx plus wtt into d by dwt. dx is equals to d by dx plus wx into d by dw plus wxx into d by dwx plus wxt into d by dwt. The partial derivatives wt, wxx, wxt and wtt here should be expressed in terms of x t w wx by means of relations equation 1 and equation 2 and those obtained by differentiation of equation 1 and equation 2. Example: consider a nonlinear heat equation with a source of general form dw by dt is equals to d by dx into f into w into dw by dx plus g into w. Let it be equation 4. Consider differential constraints of simple form dw by dt is equals to phi into w. Let it be equation 5. Equations 4 and 5 are special cases of 1 and 2 with f is equals to wt minus f into w into w square x minus g into w by f into w. Phi into w minus g into w minus f dash into w into w square x by f into w. G is equals to phi into w. The functions f into w, comma g into w, comma and j into w are known in advance, are unknown in advance, and are determined in the subsequent analysis. Find partial derivatives and total differentiation operatives. Wt is equals to phi, Wxx is equals to f, Wxt is equals to phi, phi naught Wx, comma, Wtt is equals to phi, phi naught. Dt is equals to d by dt plus phi into d by dw plus phi naught into wx into d by dwx plus phi 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 naught d by d to dwt. X is equals to d by dx plus wx into d by dw plus f into d by dwx plus phi naught into wx into d by dwt. We insert the expressions of dt and dx into the compatibility condition dtf is equals to dx square dg and rearrange terms to obtain f into d by dw into f phi dash by f into wx square plus phi minus g by f into phi naught minus phi into d by dw into phi minus g by f is equals to 0. In order to ensure that this equation holds true of any wx, one should set d by dw into f phi whole dash by f is equals to 0. Let it be equation 6. Phi minus g by f into phi naught minus phi into d by w into phi by g by f is equals to 0. Assuming that f is equals to f into w is prescribed, we find the solution of equations 6. gw is equals to a plus c into f by f into integral f dw plus b. Phi into w is equals to a by f into Integral f dw plus b. Let it be equation 7. We substitute dw from 7 and in equation 5 and integrate to obtain integral f dw is equal to theta into x e power at minus b. Let it be equation 8. On differentiating 8 with respect to x and t, we get Wt is equals to ae to the power of at into theta slash arrows f. Wx is equals to e power at theta dash x slash arrows f. On substituting these expressions into equation 4 and taking into account equation 7, we arrive at the linear constant coefficient equation theta dash x plus c theta is equals to 0. Reference AD Polyanin and VFZ7 Handbook of Nonlinear Partial Differentiation Equations Chapman and Hall CRC Press 2003. Thank you.